Solar panels, wind turbines, electric cars. Are they really clean? You have probably heard that solar panels and wind turbines are clean energy. No smoke, no pollution, no CO2. Good for the planet. But here's a question most people never ask. Where do solar panels come from? What are wind turbine blades made out of? What happens to an electrical car battery when it dies? When you start asking those questions, the answer gets more complicated and more interesting. Clean energy isn't a lie, but it isn't how the whole story either. Today we are going to look at what clean energy actually means and how it works at the physics level and what it honestly costs. First, what does clean actually mean? When scientists and governments talk about clean energy, they usually mean one specific thing: low carbon dioxide emissions during use. A solar panel, once installed, produces electricity without releasing CO2. A wind turbine, once built, spins and generates power with no exhaust, no smoke, no burning, compared to a coal power plant, which releases CO2 every single second it runs. Solar and wind are dramatically cleaner. That part is absolutely true, but notice the key phrase, during use. Making a solar panel, building a wind turbine, mining the materials for a battery, all of that requires energy and resources. And right now, much of that energy still comes from fossil fuels. So the real question isn't just what comes out of the chimney while it runs. It's what is the total cost over technology's entire life. Scientists just call this a life cycle analysis. That is the lens we're going to use today. How solar panels actually work and why they can't be 100% efficient. A solar panel does something remarkable. It converts light directly into electricity with no moving parts, no burning, no turbine. But how? Every solar panel is made mostly from silicon, the same element found in sand. Silicon is a semiconductor. It sits in a special zone between materials that conduct electricity easily, like copper wire, and materials that block it completely, like rubber. That middle ground property is exactly what makes it useful. Here's the key mechanism, called the photovoltaic effect. Light is made of tiny packets of energy called photons. When a photon from the sun hits a silicon atom with exactly the right amount of energy, it knocks loose one of the atom's electrons. That electron is now free, and if you arrange the silicon in the correct way, those freed electrons all flow in the same direction. A river of flowing electrons is exactly what electricity is. No combustion, no steam, no moving parts. Just light, silicon, and physics. But here's something fascinating that even most adults don't know. There's a hard physical limit on how efficient a silicon solar panel can ever be. No matter how good the engineering gets, it's called the Shockley-Queisser limit, and it caps every single junction silicon panels at about 33% efficiency. Why? Because sunlight arrives in a wide range of photon energies. Photons that are too weak can't knock loose an electron at all. Their energy is wasted at its heat. Photons that are too strong knock the electron loose and waste the energy as extra heat. Silicon can only perfectly capture a narrow band in the middle. This isn't a solvable engineering problem. It's a law of physics. The best commercial solar panels today reach about 22% efficiency. Cutting-edge multi-layer panels, which stack different materials to capture different parts of the light spectrum, can push past 30%. But they are expensive and mostly used in space satellites where cost matters less than performance. Now, the costs. Turning raw sand into solar-grade silicon requires heating it to around 1,500 degrees Celsius. a process that uses significant energy. Solar panels also require small amounts of silver for the electrical contacts, and some older panel types use cadmium, a toxic metal that must be carefully handled at the end of life. The good news? A solar panel pays back to its carbon debt, the emissions from manufacturing it within about 1 to 4 years of operation. Since panels last 25 to 30 years, they spend most of their life producing genuinely clean electricity. How turbines actually work, and why you can't extract all the wind's energy. A wind turbine looks simple. Wind blows, blades spin, and electricity comes out. But the physics underneath is more surprising. First, why do the blades spin? Not because the wind pushes them from behind. That would be very inefficient. Instead, each blade is shaped like an airplane wing, curved on top, flatter on the bottom. When the wind flows over the shape, it moves faster over the curved top than the flat bottom. Faster moving air has a low pressure. That pressure difference creates lift, just like it lifts an airplane off a runway. The lift pulls the blade forward in a circle. Wind turbines don't get blown around. They fly in place. Second, here's the most counterintuitive fact about wind energy. You can't extract all of the wind's kinetic energy, and if you tried, you would destroy the turbine's own power source. Think about it. If a turbine removed 100% of the energy from the wind passing through it, the air would stop completely on the other side. But stopped air means no more wind flowing through. The turbine would have choked itself. In 1919, a German physicist named Albert Betz did the mathematics and proved that the theoretical maximum is 59.3% of the wind's energy, now called the Betz limit. You must leave enough energy in the wind to keep it moving through and away. The best modern turbines reach about 45 to 50%, impressively close to the physical ceiling. Now, here's a fact that explains why a wind farm location is everything. The power a turbine can generate is proportional to the cube of the wind speed. That means if the wind speed doubles from 5 meters per second to 10, the available power doesn't double. It increases by 8 times. A site with exactly stronger average wind produces dramatically more than electricity. This is exactly why engineers seek out coastal headlands, mountain passes, and open ocean, places where wind is constantly fast. And it's why offshore wind farms, despite being far more expensive to build, are so much more productive than land-based ones. The materials problem, turbines' blades, must be both light and extraordinarily strong, able to survive decades of storms and stress at extreme scale. Some blades are over 100 meters long. They are built from fiberglass and carbon fiber, which are excellent engineering materials but are nearly impossible to recycle. When blades reach the end of their life, most currently go to landfill. Inside the turbine's generator, powerful permanent magnets from rare earth elements, especially neodymium, are essential. Most of the world's rare earth elements are mined in China, a process that produces toxic wastewater. Engineers are actively working on turbine designs that reduce or eliminate rare earth requirements. Electric cars and the mining problem. Electric cars produce no exhaust. On the road, they are genuinely clean, but the battery inside requires lithium, cobalt, and nickel, metals that must be mined from the ground. Lithium mining in South America's Atacama Desert uses enormous amounts of water in one of the driest places on Earth, affecting local ecosystems and communities that depend on groundwater. Cobalt mining, much of it in the Democratic Republic of Congo, has been linked to serious environmental damage. And when a battery reaches the ends of its useful life, typically 8 to 15 years, recycling it is genuinely difficult. An electric car battery is not one material. It's a complex structure of many different chemicals layered together, and separating them to recover the valuable metals is energy intensive and expensive. Scientists are working hard on better recycling methods, but the technology isn't fully there yet. This is one of the most active areas of material research in the world right now. The numbers. How much cleaner is cleaner? Here is where the life cycle analysis produces a clear answer. Scientists measure emissions in grams of CO2 per kilowatt hour of electricity produced, accounting for everything from mining the raw materials to building the technology to using it to disposing of it. The results are striking. Coal, approximately 820 grams of CO2 per kilowatt hour. Natural gas, approximately 290 grams, or approximately 20 to 50 grams. Wind, approximately 7 to 15 grams. Nuclear, approximately 12 grams. Wind power across its entire lifetime, including manufacturing, produces about 50 to 100 times less than CO2 than coal per unit of electricity. Solar is 15 to 40 times less. These are not small differences. They are orders of magnitude. So, is clean energy actually clean? Here's the honest scientific answer. Cleaner? Yes. Perfectly clean? No. Every energy source has a cost. The silicon in your solar panel was refined at 1,000 degrees. The turbine blade in a landfill still exists. The cobalt in your car battery came from somewhere difficult. These costs are real, and pretending they aren't doesn't help anybody. But when you look at the full life cycle, from raw material to end of life, solar, wind, and nuclear produce dramatically less harm than the alternative. And the problems that remain, blade recycling, battery chemistry, rare earth dependence, are engineering challenges, not fundamental physics limits. People are actively solving them. Clean energy should really be called much cleaner energy. That distinction matters because it means we need to keep pushing on manufacturing, recycling, and responsible mining, not just declare victory and stop thinking. Solar panels obey a physics limit. That means they can't ever be more than 33% efficient, no matter how good the engineering gets. Does that surprise you? What would you do with a panel that captured 100% sunlight if the laws of physics allowed it? Tell us in the comments.